Welcome to Lecture 8. Today we're going to begin looking at how electrons fit around and inside atoms and get into something called electron configuration over the next few lectures. So without further ado, let's get my notes in front of us. So what I want to do is start by asking a question. What does carbon atomic mass 12 with a zero charge look like? It's a weird question, but it's an important question. We don't usually think about how atoms actually look. We like to think about how they look in bulk, how taking a bunch of carbon atoms, trillions of carbon atoms together, starts to make things look according to our eyes. It's impossible for our eyes to see single atoms on their own. But we've learned through several experiments how they're probably arranged and I guess what the anatomy of an atom actually is. So let's go through this. So the question really is asking, when we ask what it looks like, is how are the constituents or the subatomic particles of the atom arranged? So how are the subatomic particles arranged? Now, to recap, we've brushed on this a little bit, and we said when we described subatomic particles at first, we said protons and neutrons are located in the nucleus. Electrons, these low mass particles, are located in something called orbitals. It turns out that if we want to think about how these things fit together, orbitals surround, and that's where the name comes from, orbit. Orbitals surround, goodness, clean that up a little bit, and orbit the nucleus. So the nucleus. Let's go ahead and try to draw that. So a nucleus with, what do we need again? We need 6 protons and 6 neutrons for our carbon-12 atom with a zero charge. We've talked about that before. So 6 protons and 6 neutrons need to fit into the nucleus. So a way to think about it that's going to have a lot of shortcomings, but is at least helpful for this discussion because we're on 2-dimensional pieces of paper, or I guess 2-dimensional screens, is we're going to have protons and neutrons sort of next to each other. And you can think about these things as tiny mass-bearing spheres. So these tiny mass-bearing pool balls, let's say, are trying to fit together. I'm really going to embrace the pool ball model and have them get close to each other. But pool is, again, a 2-dimensional, I mean, I know the billiard balls are 3-dimensional, but we put them sort of on a flat plane, which is the pool table. And that's how I'm going to draw them here. There's a shortcoming to that. These things are going to ball up in as tight of volume as possible. So having a 3x4, matrix is not correct. So you want to picture these things as balling up even tighter into more of a spherical matrix, but at least we get the idea that these things get close to each other. And there's something I want to illustrate here. We often have, you could think about it as alternating protons and neutrons. And the reason why we do that is because the neutrons stabilize protons held in close proximity. So whenever we want to put 2 neutrons close to each other, which is the case for the nucleus, we're trying to pack all of these protons as tightly as possible. They're all positive charged 1 subatomic particles. They're all sort of repelling each other. Neutrons help allow us to pack them in as tightly as possible. Even if you look at helium, just as an illustrative example of this, well, hydrogen has 1 proton. It typically has 0 neutrons. Helium, which I'll just show as its atomic symbol, is the next element on the periodic table. So it has 2 protons, because we're going to just traverse 1 proton, 2 protons, 3 is then lithium, and so on and so forth. But as soon as we introduce that second proton and put that second proton in the nucleus, now the typical mass for helium is to have an atomic mass of 2. So it's going to counter, whereas hydrogen typically has 0 neutrons, helium now typically has 2 neutrons to help us hold those 2 protons in close proximity with each other. Okay, anyway, back to the discussion. We have protons and neutrons packed as tightly as possible together. The neutrons help us to put this positively charged subatomic particles in close proximity with each other. And so this line, this circular line on the outside, is sort of the nucleus. And I say sort of because, again, we're in 3 dimensions. We want to pack these things into more of a spherical-like architecture. But hopefully you get the idea. We pack them in close. The nucleus is a very tight, and I like the word dense, part of the atom. Very dense. And I'll emphasize that again, but I'll say it now. Okay, moving on to the other part of the atom is we have the orbitals. Orbitals. This is the space surrounding the nucleus where electrons are located. Okay, now for now, what we're going to do is just consider this as a circle or a sphere. So there's going to, it's an approximation. When you look at, I know some of you have seen the various shapes of orbitals, and we will too by the end of this lecture, and you're bothered by this, but the average conglomeration of many of the orbitals, it starts to look spherical as it expands from the nucleus. So this circle is, in fact, our orbital, and if you look, I've filled it with 6 E minuses. I don't want to put circles around the E minuses like I did for the protons and neutrons, because electrons are not as billiard ball-like as their subatomic particle cousins, the protons and the neutrons. So they kind of float around in this orbital which surrounds the nucleus. Now, to scale, let's add the nucleus to our atom. So I'm drawing a deliberately small dot in the center of our circle. I'm going to come out from red there. That dot is the nucleus at the center of the atom. It's very small. Hopefully you've made that observation from our picture. The nucleus is very small. The orbitals, in contrast, are large. Now let's be better about quantifying or sort of describing the property of size here. Okay, we've talked about physical properties related to size. What we're talking about with our large and small words is we're talking about a large volume for the orbital and a small volume for the nucleus. Okay, so we're talking about volume, we're not talking about weight or mass. So it turns out that the orbital has a large volume, and it's not as large as me, but it's large relative to the nucleus. The orbital has a large volume, but let's think about the mass of the orbital. Okay, the mass has 6 electrons. So our orbital space only has 6 electrons, which is roughly, has a mass roughly equal to 6 over 2,000, which is roughly 0. So we have a large volume and a low mass. We would say that the orbitals are low density. The orbitals have a very low density. Conversely, the nucleus has a small volume, but has 6 protons and 6 neutrons for a mass equal to 12. I don't need the division sign here because each of these subatomic particles is 1 AMU, so it has a mass of 12 AMU. The nucleus has a large mass and tiny or small volume. I've alluded to this twice now, but let's get back to the definition of density. So density is equal to mass over volume. We discussed that in the first lecture, mass over volume. So with this in mind, if our mass goes really high, as in the case of our nucleus, we've put all of the massive subatomic particles in the nucleus. If our mass goes really high and our volume gets really low, anytime you make the numerator big and the denominator small, the output is big. And this is density. Sorry, I ran out of space. So the density is going to skyrocket and get huge because the volume is decreasing, the mass is increasing. We have a really dense nucleus at the center of a really low density orbital system. Because conversely with the orbitals, orbitals have a very low mass and a very large volume relative to the nucleus. So that's the picture I want us to carry. I want us to carry that the majority, that is nearly all, let's write it, let's even write the word nearly all. Nearly all atomic mass is from the nucleus. And nearly all atomic volume is from the orbitals. This should bother us somewhat. This is uncomfortable to kind of think about reality in this way, but really all volume that we experience, everything that occupies space is defined by orbitals, because the things that we're interacting with mass and volume are matter-bearing objects, things with a nucleus and orbitals. So the volume of any object that we experience is the volume felt by the orbitals interacting with the orbitals in whatever we're using to interact with them. Similarly, whenever we notice mass or something feels heavy, that's all coming from not the space that it occupies, but by the amount of subatomic particles in the nucleus of these various atoms. So again, that should make us feel uncomfortable. I feel like, though, even though the nucleus is really small, it's kind of intuitive. We're kind of packing these small subatomic particles together. You can think about it as averaging into a larger billiard ball or a larger sphere made up of these small subatomic particles. But the orbitals are a bit strange because the orbitals harbor all of the electrons and they have a large volume. But what are the electrons? because I said they are so low mass, I don't want to consider them as billiard balls. Why do they need so much space? This is where we see this really counterintuitive nature of atoms start to appear. So let's start talking about orbitals more. So orbitals are regions of space an electron can occupy. So regions of space that an electron can occupy. Okay, so there's a few words in here that are important. Region, I really like the word region, and what this describes is a shape with, because we're talking about the three-dimensional reality, shape with a volume. Now, occupy is a strange word, and I write here that the electron can occupy the shape or volume defined by the orbital, but it sort of will occupy that entire space. The electron, but let's think about it for now, as the electron can be anywhere inside the orbital. And if it's occupying an orbital, according to what's called the Heisenberg uncertainty principle, it sort of has to be everywhere inside that orbital. We can't know for certain its exact points without losing some other information. And as a result, we just sort of take an average of the information that we can know and say that it's occupying everywhere inside the orbital. Okay, let's back away from that and get to something that hopefully we can grasp a little bit better. And that is the three-dimensional shape of orbitals. Okay, so maybe you've seen this before, but there are what are called s orbitals, s as in the letter S, and p orbitals, p as in just the letter P. There's s and p orbitals, and they have a three-dimensional shape. S has the shape of a sphere. Now, I'll do my best to draw a sphere on a two-dimensional plane. So just a circle, and then you can like add whatever features you want to make sure that you know that it's actually a three-dimensional shape. Now, p orbitals, I think strength training has sort of evolved enough so that this actually doesn't work as well, but we'll still stick with it. They're called the dumbbell-shaped orbitals. They're kind of two distorted ovals that are connected at the center. So these are p orbitals. Now they're three-dimensional, so there's a three-dimensional component where you can think about these as two spheres connected in the center that are sort of distorted a little bit. And people say it looks like a dumbbell because you could grasp the center of it, I suppose. So these are the shapes of the orbitals. Now this is, I should highlight this. This is one of those things where if you're looking for what minimally to take away from this lecture, this is one of those things. Now, many of you have probably seen this before, or at least seen what the shapes are. Let's talk about where the shapes come from. And the answer is mathematical equations called wave functions. Mathematical equations called wave functions. So a wave function is denoted with the Greek letter psi. So this is psi. This is like our letter y for a linear equation or some sort of algebraic equation. Whenever we say psi equals something, That is to say, psi equals a wave. We just use psi. Whenever we see the letter psi, we're thinking, okay, now we're going to talk about wave mathematics, or mathematical equations called wave functions. Where if you've taken enough calculus, you know, function is just kind of an equation that describes maybe that we can plot on a graph or study using calculus, derivatives, integrals, that sort of thing. And that's exactly what we're going to do here, but with much less hard mathematics. Okay, so the wave function for an s orbital can be actually plotted. Okay, so I'm just going to graph it on some traditional Cartesian coordinates where we have a y and an x. And then what it looks like is it just looks like a hump that starts at the origin, goes back, hits the x-intercept, and stops. Now, we can do the exact same thing. Similarly, we can do the exact same thing for a p orbital. And it's going to have a different shape. It's going to start at the origin, pass through y equals 0, and then hit into y equals 0 again. You notice we have a sort of similar width. Now, if you look at the p orbital wave function, it looks like a wave. Now, the wave function for the s orbital is also forming a wave. We're just not making it through an entire period before we finish this wave function. So we use some complicated mathematics called wave function or wave mechanics to describe these graphs. And now what we do is we take these graphs and we actually square the function that gave rise to this graph to get a shape. So what I want to do is I want to take psi squared for the s orbital, and it will give, if I take psi, which defines the mathematics that gave us this shape, and I just square that mathematics, I'm going to get a shape. And that shape is going to look like a sphere. So a sphere forms. Now, one way you could think about it, I'll just mention this briefly, is you could think about that when you square it, you kind of take this curve and you just roll it over 360 degrees, sort of about the x-axis. I'm going to get rid of that. Just a way to think about it. The important thing is that we can take psi to set that equal to a wave function. The waves are going to look different between the s and the p orbitals. When we square that wave function, that's when we get our shape. The same thing is going to happen for our p orbital wave function to give rise to our dumbbell, quote, dumbbell-shaped orbital. Okay, so some properties start to exist when we make the shape of our orbitals. And these are some, and these properties are really important to understanding how atoms actually look. So here are some important properties. First, is the number of electrons. How many electrons can a single orbital hold? Or how many electrons can exist or occupy a single orbital? Really important question, worth highlighting. Now, some of you are thinking back to some high school chemistry and you're like, oh, I know, sometimes it's 2, sometimes it's 6, sometimes it's 10, sometimes it's 18. It's always 2. Always 2. Okay, now I know some people want a refund on their tuition at this point, but hear me out. The answer to this question, how many electrons can occupy a single orbital, is always 2. Now, to make some sense of all of this, given what we know about s and p orbitals, or what many of you have seen, if you haven't seen this, don't worry, we're going to go through it right now, is that some orbitals exist as multiple degenerate suborbitals. Or really, some orbitals can form multiple degenerate suborbitals. Truly, each orbital can only hold 2 electrons. It's just using tricks in mathematics. It's not really tricks, it's just realities in mathematics. We can see that actually, instead of just 1 p orbital forming, there can be 3 p orbitals. They all have the same energy, and we can, in each case, fit 2 electrons. Now, with this important caveat to our number of electrons, we see that the observed number of electrons in an orbital is equal to 2 times the number of suborbitals. That is, if you can form 2 suborbitals, and each of those suborbitals can fit 2 electrons, then you can have 4 electrons total. Now, where does this come to pass? S orbitals do not form suborbitals. So s orbitals always, whether you want to be really strict in your definition, you say 2 electrons. Or if you want to say, okay, how many do we observe in this set of this type of orbital? It's always 2. S orbitals, always 2 electrons. P orbitals exist now as, or we can form, p orbitals can form 3 suborbitals. Maybe this bothers you. Maybe you're like, why? Well, let's look briefly at it, but we're not going to go into the full mathematical derivation for each of the 3 suborbitals. But one way of looking at it is just thinking back to the Cartesian axis. We can have p orbitals, or dumbbell-shaped orbitals, that are parallel to the x-axis. This would be the px orbital. We can have a p orbital parallel to the y-axis. This would be the py orbital. Or we can have a p orbital coming out at us by way of the z or z axis. This is going to be the pz or the pz. I ran out of a little space in my y orbital. I just want to clean up that label. So if I'm honest with you, there is no p orbital. There is a px orbital, a py orbital, and a pz orbital. There's no just p orbital. There's always 3 that you can form. If you try to do the same thing for s, it actually exists in the center of our plot. You can't move it to the x, y, or z axis. It's just a sphere. So thinking about it graphically, you can see why the math can't find a way to put it on a different axis, and there's only 1 orbital. So each of the px, py, and pz can hold 2. So s can't form suborbitals. I'll leave this here. It's not super important that we fully digest that. But all 3 of the p orbitals can hold 2 electrons each. So we can put 2 in the px, 2 in the py, and then 2 in the pz. Or we can say that we observe 6 electrons total in p orbitals. Now, why is that? Why can't we really tell the difference when we're observing these things, whether an electron is in the px, the py, or the pz? Well, the reason why is because the p orbitals are degenerate, and I've used that term a few times in this lecture. Degenerate means the same energy. We'll get to energetics and energies in chemistry a little bit later, but basically when things are going to interact with each other in chemistry, they try to go to the thing that has the lowest energy or the lowest energetic barrier to entry. So if an electron has a choice between a px, a py, and a pz, and it's going to pick one that has the lowest energy. And we'll look at that more in electron configuration later. But because these three orbitals are degenerate or of the same energy, then the electron's going to not really be able to tell the difference. We can't tell the difference. It's just going to pick one at random. Degenerate, the same energy. That's why we appear to observe 6 electrons at the p energy level. Okay. So what about the other types of orbitals? So moving beyond the s and the p orbitals. I'm not going to make you worry about this for this class. That'll be the topic of inorganic chemistry and structures and reactivity. We have the d orbitals, and these have 5 suborbitals, or they can house 10 electrons can be observed in the full d orbital system. Now, truly, d orbitals exist as 5 suborbitals, and the mathematics gets a little bit more complicated. Similarly, f orbitals also have suborbitals. They're made of 7 suborbitals. 14 electrons can exist in total in the f orbitals. Okay. Let's just finish up really quick with some properties of, well, yeah, let's finish really quick with properties of the p suborbitals. Number 1, they're degenerate. That's an important thing to carry with us. They have the same energy. Number 2, they have the same shape, but with different orientations. Number 3, they're what's called orthogonal. Our math types in the class will recognize that word. For us, let's just suffice it to say they don't touch each other. Number 4, the most important thing is that each can hold 2 electrons. Okay, that'll do it for today. So we looked at orbitals. We covered really all the types of orbitals I want to cover in this class. And up next, we'll look at electron configuration. So I know some of this was maybe a little bit deeper than you had thought about in the past regarding electrons and orbitals, but I'm trying to make it more correct and approach more of kind of a rigorous understanding of these things.